Well, thank you very much for inviting me to talk to you, and thank you very much for welcoming me in your wonderful school, and for setting up this experiment for the first time for me. So let me first introduce myself. My name is Matthias Dörzapf. I have in mathematics I've worked in various areas. As a student I studied at a university in Germany doing maths and physics. Then I came to Cambridge doing a master's course at Cambridge in theoretical physics, in elementary particle physics. Then I did a PhD at Cambridge in string theory. After that I worked in financial mathematics, first in Frankfurt, then here in New York for a while. Then I went to Harvard University and I worked in algebra there, continued doing a bit more financial mathematics, and for the last 20 years I've been back in Cambridge in England, doing again quite a lot of algebra, but also again theoretical physics, elementary particle physics, and as you know Cambridge is very strong in that field in particular. So why do I say this? I think it's relevant to understand that a mathematician actually can use his or her skills in very different areas of mathematics, and it's very important that you do this. A lot of the big finds in mathematics were really found by people who sort of transferred the skills they've learned in one area to another area, and it's very, very important that you experience different areas in mathematics. It's very exciting, and mathematics is really offers these opportunities. So the maths I want to introduce you today is actually very recent mathematics. It's only about 30 years old, and that's even more amazing that mathematics that is 30 years old is already now being taught at university at probably second or third year level, and students would be expected to be able to work with this theory in exams within 10 or 15 minutes. Calculations that 30 years ago would have been in a research paper and would have taken 50 pages to explain. So that's actually amazing that mathematicians have this ability to really think through a theory and sort of present it in such a way that you really restrict yourself to sort of the essential points that make it work. So the question I want to raise today is, what is risk? That's a really grand question. Risk is around us all the time. We all, people talk about it all the time. Some of us love it, some of us hate it, some of us can't be bothered about it. But what is it? How do I quantify it? What really is it? So let's take a very simple example. You go to a shop, you buy a CD player, and then you're being asked, do you want to buy insurance, or do you want to buy an extended warranty? And of course this costs something to buy it. And that's the risk you want to insure. Which risk? Well, the risk that the CD player you've just bought might stop. Okay, so it's that's the risk, it might stop. They won't sell you an insurance for against the fact that, say, your batteries might stop. Why not? I mean, what's the difference between the battery stopping and the CD player stopping? And that's because the batteries, it's certain they will stop. They will stop once you have used up the energy that is stored in the batteries. The battery will stop. They're empty, and nobody will buy insurance against the fact that you might use up the energy in your batteries. In the same way as nobody will insure you against the fact that you might have finished your beer or your lemonade or something. And that's exactly the same. So here you've got certainty. Your battery is empty at some stage. That's certainty. No risk attached. The CD player, it will ultimately stop. We know in 10,000 years it will have stopped. But you don't know when it stops. So the uncertainty is the problem. The uncertainty is the risk. So when we, in the following 40 minutes, talk about risk, keep in mind, we are not talking about the fact that the CD player stops. We are talking about the fact that we don't know when it stops. The uncertainty is the risk. And we want to quantify the uncertainty. We want to somehow price the uncertainty. Because, of course, the insurance company who wants to sell you this insurance, they need to price it correctly in such a way that they can actually really make business out of that. And you want to be offered a fair price so that you can afford it and you don't overpay. So how do we quantify this kind of risk? So I will take you first through sort of this idea, what is risk? We'll give you a few examples. And then I will introduce a few mathematical ideas how this risk should be modeled. There will be something called utility functions, and then in one particular a simple setup, which I will call the binomial tree. I will actually show how to price a very simple risky gamble, and then I will generalize this to a bigger theory, which will ultimately lead to something called the Black-Scholes formula. And there was a Nobel Prize for this in '97, so it's very, very recent mathematics. Okay, let me give you the following gamble. So I hope you can see this. So the gamble costs you $1 today, and with a 50% chance you get $1.10 back, and 50% chance. Oh, okay.
Smart.
Yes. And a 50% chance you get 80 cents back. On average, if you take the average here with these probabilities, you get 95 cents back. Is it risky? Yes, it is risky. There's uncertainty. It's a risky gamble. Okay, you agree? It's risky. If I give you the following gamble, there are actually arrows. They're sort of yellow, but you can hardly see them. So if you look at the following gamble, this gamble has the same average. You pay $1 today. With 100% certainty, you will get 95 cents back tomorrow. Is it risky? No. No uncertainty at all, not risky. Is it a good gamble? No. So this is risky, this is not. They have the same average. So my point is actually, it's not the average that matters. It's the fact that there's uncertainty. I give you another one. Same average again. You pay $1 today, with 99.999% you get nothing. With 0.0001% you get $95,000 back. The average is again 95 cents. So like the other two, is it risky? A tiny bit. There's a bit uncertainty. You will lose. I can guarantee that everyone in here will lose. There's one lucky one somewhere out there who will win, but everyone else will lose. So the most risky gamble is this one. This one is certain, and this one has a tiny bit of risk. Okay, so risk is really the uncertainty, and that's what we want to quantify. So the risk is the uncertainty in the outcome of a gamble. How can we sort of determine today's price of a risky gamble? How can we do this? So I want to offer you the following gamble. I will say 50% chance you get $1, 50% chance you get nothing. How much would you individually be able to pay for that? So that's a question for each of you individually. How much would you pay for it? 50% chance $1, 50% chance you get nothing. Are there some people here who would pay more than $1? Well, I hope not. But how much would you pay? What do you think? 50 cents, yes. A lot of people say 50 cents. What have you done to work this out? You took the average under these probabilities. You said, isn't that a reasonable assumption to pay 50 cents? Somebody is unhappy paying 50 cents?
Not particularly in this case, but if it's a larger sum than $1 and 0, I'd probably go to like 25 cents.
Yes.
So it's like a fourth.
Yes, because you want to somehow have the chance of making money out of it. If you go for 50 cents, then you know, if you do this a million times, you actually don't gain anything out of it. But if it's a large amount, you're quite right, and you know, it would actually matter to you. So you already realize that actually different people will have different answers. And it will depend on your own sort of value you attach to it. And it's exactly what you said, it depends on the value you attach to the outcomes. It depends on a lot of factors. The more you think about it, the more you realize that actually there are lots of factors influencing exactly the decision. There might be a few people who would actually pay more than 50 cents. And why would they do this? Because they like the thrill, they like the environment. You see, if you're in a casino where they give you free cocktails and all these sorts of things, and then suddenly they make you feel so good about this that you start paying more and more for this gamble. And so what matters is not only sort of the average and what are the outcomes. What matters is really in that situation the value you personally attach to the outcomes and to the whole gamble. And that's something we try to capture in mathematics using something called the utility function. The utility function describes how a consumer values the goods in terms of your own preferences. Unfortunately, we don't know your utility function. So, if you ask me now, what is your own personal utility function, I can't tell you. We don't know what these functions look like. However, we know a lot of properties of those. And, some of those, we simply assume that these are axioms for these utility functions. And there's a whole list of axioms we normally assume. I give you just 2 axioms. One of them is called the completeness, meaning that we assume that the utility function is such that you can always compare 2 possible goods or outcomes or whatever you want to attach preferences to. And the other one is called transitivity. Do you know what transitivity is? Have you heard of transitivity? You should know transitivity, I guess. You know it from algebra, isn't it? Say A is less or equal to B, B is less or equal to C. Therefore, you know already, you don't need to check, you will know A is less or equal to C. So that's transitivity. For preferences, for the utility function, we assume the same. You prefer meal A to meal B, and meal B to meal C. We assume you prefer meal A to meal C. That's an axiom we put into the utility function. It might not be true for everyone. Not everyone is behaving rationally, but we assume that normally that would be a property of utility function. There are a number of other axioms and assumptions we make on utility functions, and in this way we try to model human behavior. Then there are some properties. Say, when you said that you would try to pay less than the 50 cents, because obviously, if you do this several times, you want to gain money out of it. You're actually called risk averse, and the risk averse person would then have a concave utility function. And this then simply has the following effect. So concave, that's this sort of curvature, so it looks like a cave when you look at it. So that has the following, the following effect that, for example, you would value the difference between $200 and $100, you would value a lot. And I'm sure, for each single one of you, having $200 or $100, there's a big difference. It's quite absurd that if I tell you then, how do you value the difference between $200 million and $100 million? And you would probably attach very tiny difference to the two, because these are such big sums that you can afford anything, anyway you want to afford. And therefore, it makes hardly any difference to your utility function, having $100 million or $200 million. But it makes a bigger difference to have 200 or 100. So that's a concave utility function. And most people would have concave utility functions. So most people are probably risk averse. Those who just take averages, like what you suggested before, I would call this risk neutral, because you really just take the average and you really don't mind the risk. And somebody who has a convex utility function would be called risk loving. And what people then do, so whenever you take decisions, then you optimize over this utility function. That's how you decide on your preferences. So there's a whole theory, there are whole books written about utility functions, and you can study those, and that's great. However, for the actual problem we now want to look at, how do we price such a particular gamble? This is actually really bad news now, because the price for this gamble I gave you before depends on your own utility function. Everybody would come up with a different answer. So you could say that means this is actually an unsolvable problem, and therefore end of talk and you can all go home. So some of us are risk averse, some of us are risk loving, and some of us are risk neutral. A real problem. However, there is now one thing I want to assume, one property I want to assume for everybody's utility function. And I want to convince you, if I assume that each single one of you has a utility function that prefers more to less, then we can solve the problem I have given you before in a particular setup. So I'm now assuming that everybody's utility function prefers more money to less money. I appreciate that's not true for everybody, but it's probably true for most people in this room. But as I said, it's not true for everybody. But if we assume that all your utility functions would prefer more to less, then I can price in a certain setup the gamble I gave you before. And the way I want to explain this is, if I now assume that I offer you two gambles, and these two gambles have exactly the same outcomes. So if I say that I offer you the first gamble, cost today P0, and with a probability, I did it again. Okay. Okay. Cool. Okay, so the first gamble costs P0 today. With probability PU it goes up to the price PU. With probability PD it goes down to the price PD. The second gamble, in the state up it goes to PU, in the state down it goes to PD. And it costs Q0 today. So two gambles that have exactly the same outcome at time t. And today they have the price P0 and the price Q0. What do you think about P0 and Q0? So you have two gambles. They pay you tomorrow exactly the same. If you go in the upstate, they pay the same amount. If you go in the downstate, they pay the same amount.
I guess you take whichever gamble you pay less money for.
Yes, so if one of them costs less, then of course the rational person would buy the one that costs less, and then would sell it as the gamble, and would sell the gamble that costs more, and therefore gains money. So I give you a very simple example. If IBM shares today trade in London for $10, but here in New York for $11, well, you will buy them in London, and you won't only buy one, you will buy a hell lot of them. And you will sell them instantly here in New York, and you will actually gain infinite amounts of money out of that. And the interesting thing is, you would do this even if you think IBM is rubbish or IBM is brilliant. You don't care what it is what you're buying. All you care about is that it's the same gamble with the same payoff, and one is cheaper than the other one. What then would automatically happen is that, unfortunately, you won't be the only one who notices. Everyone else would notice as well. And as a result, everyone would want to buy in London. The price would therefore go up. Everybody would want to sell in New York. The price would therefore go down until they equalize. Which means if this is happening, that you have two gambles, they pay the same, they have to have the same price today. That's called arbitrage opportunities, and they don't live very long. As soon as they're discovered, they disappear for exactly that reason. So two gambles with the same price, two gambles with the same payoff have to have the same price. And this is simply based on the assumption that you prefer more to less. And the amazing thing is that we come to this conclusion independent of your utility function. Whatever your utility function is, it doesn't matter. All we need is to know is that one property of your utility function is that you prefer more to less. And I now want to go to a very simple market, and in this market reconstruct a gamble I offered you earlier when we disagreed on the price. And this simple market should have a bank account. You know how bank accounts work. You give your bank $1, and then at time t they give you back $1 plus the interest rate. So if the interest rate is 5%, you get back at time t $1.05. And that's risk-free. It's meant to be risk-free. Banks are not meant to default, but obviously sometimes they do. And then in this market we also have one asset. So we trade only one thing. You can only buy one thing. Let's say these are apples. Apples that do not rot, that you can keep forever. And that's just the commodity we have. And these apples, they cost today the price S0. And in the upstate, so with a probability PU, the price will go up to U times S0, where U is the factor that determines the price then tomorrow. And with a probability PD, it goes to the downstate, and that would be then the factor D times S0. Let's say U could be 1.1, D could be 0.9. So if apples cost today $1, they could go then at time t to $1.1 or $0.9. So that's the market, and I appreciate that that's a very simplified model. I only allow for 2 possible prices tomorrow, but later on we will generalize this to a continuum of prices. So, but for this simple model, the advantage is here that the equation will be very simple to solve. So that's the market we are trading in. We only have the bank account and we have these apples. And within this market, but before we continue, I want to simplify one thing. I want to put interest rates to 0 just to make the equations easier. So the bank account will simply go, you put $1 in, you get $1 out. And in fact, that's the reality nowadays almost anywhere in the world. So, good. So in this market, I will now go back to offering you a gamble, just like before. And this gamble is now linked to the price of the apples. So if the price of the apples go up, probability PU, the gamble will pay the amount capital PU. If the price of apples goes down, then you will pay PD. So the gamble is linked to the underlying asset. And the price of this gamble today is P0. And obviously we want to work out what P0 is. I asked this question earlier and you all came up with different answers. But in the meantime, we have learned if I can construct a gamble that has the same payoff in the upstate PU, in the downstate PD, then we will all agree on the fact that this other gamble and this gamble would have to have the same price. And that's what I will do, independent of your utility function. So what is P0? Now I will try to achieve this generating a second gamble that has exactly the same payoff. I will try to achieve this by taking a combination of bank account and apples. And with that combination, I will convince you I can actually achieve this. So I take, and that's what I would call a replicating portfolio. So it's a combination of 2 accounts, bank account and Apple account. And I will try to construct it in such a way that whatever hold in bank and Apple account together will give you in the upstate PU in the downstate PD. So if I hold X1 in the bank and X2 in the Apple account, then it's 2 equations that will achieve exactly what I said. So if the world goes up in the upstate, then the bank account will give you X1, the Apple account will give you X2 times US0, that's the price of apples at time t. And I want that this matches PU. In the downstate, the bank account will still pay you X1, and the Apple account will give you X2 times DS0, because that's the price of apples then at time t. And this I want to match the downstate of the gamble. So if I can achieve that this combination of the 2 accounts, X1 and X2, will give you exactly the same payoff, PU and PD, then I have indeed created that this combination of X1 and X2 accounts will pay exactly the same as the gambler offered you, and therefore they have to have the same price today. 2 equations, linear equations with 2 unknowns. Can we solve those? What do you think? What do you expect? Yeah? Lots of possible outcomes. You could have a unique solution. You could have no solution at all. You could have infinitely many solutions. If you think it through here, you have a unique solution provided U is not equal to D. If U is equal to D, then you have a problem. But if U is not equal to D, then you have a unique solution. And I have done the calculation for you. That's the solution. And you already see that U equals D would be a problem. That's the solution. You have a unique solution. So indeed, this problem is solvable. And now I know that this account, or this combination of accounts, of bank account and apples, together will actually give you exactly the same payoff as the original gamble I offered you. And therefore, the price of this combination of accounts today will have to be the price of the gamble. And we can calculate that. Because this costs you today X1 to be put into the bank, and the apples cost you today S0, so X2 times S0. That's the price of this replicating portfolio today. And therefore, we know the price of the gamble I offered. Now that's great. So with this simple assumption that we all prefer more to less, we have managed to find a price for the gamble. So I have just summarized this. That was the gamble I offered you, PU, PD, with these probabilities. And I have now put x1 and x2 into the result, and that's the price. I've simplified it slightly. So that's the price you can get for the gamble. And that's a very nice result. But it gets even better. I will come back to exactly this formula in a second. I want to remind you again what we said earlier about risk-neutral people and how they behave. You remember risk-neutral people, they take averages. Exactly as I said earlier, you know, they simply take averages of the outcome. So if I offer a risk-neutral person this gamble, 50% chance to pay $1, 50% chance to pay nothing, the risk-neutral person would say this costs 50 cents. Okay. Let me come back to the formula we have just found. That was the formula we had found using a replicating portfolio. That was the price for this gamble in the market we had just discussed. If you look at these numbers here, these coefficients, if you add them up, they add up to 1. So if you add them up, they add up to 1. QU and QD add up to 1. And they're both non-negative, which automatically means they're also less or equal to 1. They look like probabilities. They're obviously not the probabilities PU that describe the gamble, but they can be interpreted as probabilities. And under these probabilities QU and QD, the price of P of the gamble P just looks like the average of the outcome. So if I interpret QU and QD as probabilities, then I can replace the pricing formula for this gamble simply as an average under these probabilities. And that's of course really interesting. These are not the real probabilities. Remember, you have a gamble that has real probabilities, but I have found different probabilities that make look this pricing just like the pricing of a risk-neutral person. And these probabilities, they have a name. They're called martingale probabilities. And under these are, as I said, not the real probabilities, so these are calculated probabilities. But if I change from the real probabilities to these martingale probabilities, then the pricing is simply the average under these probabilities, as if I was a risk-neutral person. And that gives us now the idea of developing the theory. How do I actually find it? So under these martingale probabilities, the person really seems to just simply take averages, seems to be risk neutral, and that also applies if you use these numbers and plug them into this equation, then you will see that this also applies to the underlying price of apples. So the person really seems to, if we change the probabilities to these martingale probabilities, then the pricing formula we develop, assuming that we prefer more to less, means that we simply behave like risk-neutral people. And we just take averages all the time. Risk doesn't matter. And that gives us now the idea of developing this theory, that we live in the risky world. In the risky world, we have an underlying market where the price of apples is assumed to develop in that way. And in this market, I offered you this gamble, where I said it goes up to PU, goes down to PD, linked to the price of apples. What is the price? And then, using our replicating portfolio, we managed to translate the risky world into what I call the risk-neutral world. And in the risk-neutral world, I found new probabilities, QU and QD, such that for the underlying apples, you simply take averages to calculate the price of today from the price from, say, next month. And then we have proven that in this risk-neutral world, with these martingale probabilities, to price the gamble, you simply take the average. Simple calculation we can do independent. Everybody would come up with the same answer, because in this world, risk doesn't cost money. You simply take averages. And then with this assumption we have made earlier, that you prefer more to less, we can now argue that we can translate it back into the risky world, and that's the price today. Very common thing in mathematics. You are working one system, you can't solve your problem there. You try to translate it into something that makes it easier. You know, you are working one coordinate system, your problem is very difficult to solve in that coordinate system. You try to translate it into another system where things look easier, rotate the system or squeeze it or whatever, solve it there, translate that. You want to solve it over the field of real numbers, you can't solve it there, maybe you solve the problem in complex numbers, translate it back in the result there. Very often we follow exactly this, the same here. We're living in the risky world, we don't know how to price it there, we find a way of translating it to a different system where we know exactly how to price it. And this is done using the martingale probabilities. We price it there, and then we translate it back to the risky world. Now, you could argue that's all great, very nice theory, but of course, it's a very simple market we can apply this to. How would it work to apply this to sort of much bigger markets that are sort of real? Let's take, apples that can have tomorrow a whole continuum of price. And not only tomorrow, that could be a price every day. So the way this is being modeled is with stochastic processes. These are processes where we basically start today, and then we say, well, from today to tomorrow, the price will develop using a particular distribution. Here I have sort of sketched it using normal distributions. So here I assume that the price of apples would on average follow some drift mu times t, but then at time t it would be a normal distribution that models somehow the possible spectrum of prices for the apples, and the width somehow of this distribution tells you how far apart the price could go. And that's how we normally model share prices, how we model price of commodities. And in these markets then, you need to do exactly the same. What we now need to do is, for this development of the price of apples, you need to find martingale probabilities that would at any point of time make sure that the average of the future is the price today. With these probabilities, which are not the real probabilities, but with these probabilities, which are called the martingale probabilities, exactly the same applies what I said before. And I just want to show you the result that Black-Scholes and Merton derived in 1974. This result is world famous. There was a Nobel Prize for it. And it's world famous. Every trader on a trading floor in any bank would have it in its pocket calculator. This is applied to contracts that are actually very important, very simple contracts. Contracts that started really in Chicago at the Chicago Mercantile Exchange, where I think farmers in the Midwest wanted to fix their prices for their goods already for the future. And why would you do this? Well, you want that your farm is safe for the future and doesn't depend on the weather. As you know, prices go up and down, and it's the farmers, but as well as the businesses, that want to agree on prices ahead of time before they actually know what the price really is. So here there are contracts like you're allowed to a contract that would give you, say, the right to buy apples tomorrow at $1.10. And you have the right to buy the apples tomorrow at $1.10, even if the price is $3. If the price is 80 cents, then you wouldn't use the contract, you would just buy the apples normally. But if the price of the apple is higher, then you would use your contract and say, look, I can buy it for $1.10. So these are normally called call options. There are varieties of those. But this is a very, very common one of the simplest contracts you can really buy. You can go to a stock exchange now and can buy it if you like. And so here you do exactly the same. For the underlying sort of stochastic process that models the price of the apples, you try to find these martingale probabilities. I appreciate here the calculation is a bit harder. It's not as before. Before it was just two linear equations, a system of two equations we needed to solve. Here it's a little bit harder, not much harder. Once you have these martingale probabilities, then you simply, with these probabilities, behave like a risk-neutral person. You take the average of the outcome of your contract under these probabilities, and that gives you this rather famous formula, which is known as the Black-Scholes formula, phi is the normal distribution here. It's not surprising that we find a normal distribution because we use it to model the development of the price. I've put the interest rate back in there, that's rho, and sigma is the width of the distribution. So you can actually calculate the price, and sometimes people tell me this is only because everybody has it in his pocket calculator. That's why this theory works. Everybody agrees on the price just because the pocket calculator says it. That's not true. Remember where it comes from. If that's not the price, then there's a replication portfolio. That will give you infinite gains. And if that's not the price, you would buy the cheaper one and you would sell the more expensive one, and you gain money out of that. And there are people out there, they notice that, they do exactly that, and they earn a lot of money out of that. And in the end, the price goes back into balance. So this is the Black-Scholes formula. There was a Nobel Prize for this in '97. Unfortunately, Fisher-Black had already died at that time and therefore missed out on the Nobel Prize. You have to be alive, apparently. Yeah, so the mathematics is really only 30 or 40 years old. They found this formula in a very, very different way. Not the way I explained it here. They found it in a very different way. They used differential equations, and it's a 50-page paper. I think it was in Journal of Finance. 50-page paper, you can read it if you like. It's quite complicated, but in fact, after that, mathematicians thought through the theory and really reduced it to the essential parts. And now it's this beautiful theory where you simply translate everything using martingales into the risk-neutral world, price it there as a risk-neutral person, and then translate it back, and you get this formula back. So I would expect even a third-year student already to be able to reproduce exactly that and to work with this theory in an exam, even within 10 or 15 minutes. Deriving this formula, as I said, 40 years ago was 50 pages paper. It's now in our third-year exam, and you are expected to do it in 15 minutes. And perhaps that's a convenient place for me to stop. Thank you very much.
Thank you so much. So, please move this away.